Oh, Ugo. Hi, Ugo. Nice to see you. Oh, I'm sorry. I guess we're not able to unmute ourselves now, right? Because we're in our talk preparation. I guess we can have a discussion after the talk.
Paweł.
Ah, Ugo. Good to see you.
Are you staying in Tallinn yet?
Yeah, I'm in my office in Tallinn.
How is the
The days are
situation?
getting a bit longer, and the weather is getting a bit nicer these days.
Well, you are on the water anyway, so it's not cold, I guess, too much.
Well, we had a proper winter this time. There was lots of snow and ice. It was nice. And I enjoyed that part because when I first arrived, the first winter was a bit of a disappointment. I thought that at least since I'm coming this far north, there should at least be, you know, some snow and ice. But this year was much better.
It's a very nice town, Tallinn. I've been there. Just
I like it very much. It's a very livable place.
Okay, shall we make a start?
Here we are.
I think it's 2 o'clock. So welcome to our seminar today. It's my pleasure, my particular pleasure, to introduce Paweł today, an old friend of mine, and I tried to figure out when we first met, but it must be maybe 15 years ago, something like that.
Oh, I think longer. I think it would have been around 2002, 2003.
Probably more, yeah.
So almost 20 years.
Probably 20, yeah. So Paweł is of course well known to all who do graph rewriting, and especially in the more categorical areas for so introducing adhesive categories to us, which was a major sort of help in sorting out some of the sort of mess, you could say, that we've created with trying to apply category theory in the double push-out approach and coming up with all sorts of interesting conditions in order to make the theory work. And then it turns out that there is a relatively standard definition for all of that, which were these adhesive categories. And only later I found out that what he actually was trying to do was something that is not completely different from what he's talking about today, namely talking about sort of categorical structures and algebraic structures of rewriting in the process. So for him, this was just a side effect of the thesis. Whereas for us, this is probably one of the most sort of interesting and helpful contributions from a technical point of view that we had over a long time. So as you can see from the title, he's still at it, and he's been at it over a long time in different places, as we just established. So he's been in Aarhus, I think, for his thesis, and then in the UK, in Southampton, and now in Tallinn, as we just heard. So he gets around a bit as well. Yes, but I give the floor to him now to tell us about the recent developments in the rewriting of using algebraic structures. Okay, so please, Paweł.
Thanks very much for that lovely introduction, Raiko, and it's a real pleasure to be able to talk at this seminar. So yeah, actually, it's an interesting piece of work because I was very much into graph rewriting, as Raiko was saying, sort of early on in my career during my PhD. But then I felt like I had enough graph rewriting for a while, so I got interested in these things called string diagrams. And then when we started thinking about how to actually compute with string diagrams, it turned out that exactly as Raiko was saying, that it was back to something that I had already known about. So it's kind of a nice piece of research that unites something that I used to do with something that I've been doing over the last 10 years or so. So this is joint work with Filippo Bonchi, Fabio Gaducci, Alex Kissinger, and Fabio Zanazzi. So Fabio is also in the audience, Fabio Gaducci. And I'm starting this talk. I want to start this talk with a bit of a kind of a high-level introduction into the problem and what is the problem and why I think it's an interesting problem. So I want to start with talking about, let's say, something which I'm going to call classical terms. So a classical term, I mean something that, you know, we used to, how we were basically taught to do calculations in mathematics, you know, from primary school. This idea has a long history. I think Fibonacci was an important figure early on, of that you know, we perform mathematical calculations using this linear syntax with variables. And since Abel, I would say that, you know, people are happy to sort of work in especially in algebra, when you write terms, when you do calculations, you understand that your terms are denoting elements of some algebraic structure, and you have some, you know, you have some equations around. You have an equational theory which allows you to perform your calculations. And of course, in the 20th century, through the formal study of logic, and also a bit later through universal algebra, helped with formalizing these notions and making them precise. Of course, we have a very beautiful categorical understanding of these, of universal algebra due to Lauvier. So classical terms, so these things that we calculate with, are actually a very nice concrete description of something that satisfies a universal property, right? So it's the free category with finite products on the signature. And so the arrows of this free thing are precisely the things that we would describe as classical terms. And of course, one thing that's been extremely important in computer science is various computational problems to do with such things. Okay, so for example, you know, if you have some algebraic structure, maybe a presentation of an algebraic structure, you might want to be able to solve the word problem. So to check whether, you know, two terms are actually equal under some equational theory. And the way this is traditionally handled, one way it's traditionally handled is with something called term rewriting. And the basic idea is that we turn our equations into directed things, and we rewrite. And hopefully, if the rewriting system is nice enough, if it's you know, terminating in confluent, we have normal forms, and this is one way to decide something like the word problem. Okay, so this is all very well understood, and I think everyone knows these things quite well. So what's the first problem? Well, I would say that, and this is something that really attracted me to string diagrams, is that terms are not really enough, right? And why is that? Well, when you think about it, terms have a built-in assumption of Cartesianity. Okay, so the fact that you can have, you know, variables in your terms, and you can repeat variables, or you might be, let's say, in the context in which you can use some variables, but you don't use them. These assumptions kind of carry an intrinsic assumption about the data that our terms talk about, and that is that this data is copyable and discardable. So this is something that's called classical data. But more than this classical data is transformed in a functional paradigm. Okay, so the idea is that basically the kinds of operations we talk about when we talk about classical syntax are implicitly assumed just by the way the terms are structured to be total and single valued. Again, and these assumptions are not particularly fit for purpose. So in many examples, in many different application areas. So one famous example is, you know, quantum foundations, quantum computing, where we work with qubits that cannot be copied. So the data there in that setting is not classical. And computing, of course, famously, functions aren't total. And this is the foundational observation of recursion theory. And more recently, some of these insights also come from control theory. If you want to understand a computational system in a compositional way, so that we want to understand you know, if we have some computational system and we want to break it up into pieces and understand the behavior of the whole by understanding the behavior of the pieces and how they're interconnected, so this kind of an idea of compositionality. Well, it turns out that when you try to do this, very quickly you realize that a functional understanding is not sufficient, right? So functions aren't compositional. And typically what happens is you end up with relational structures, right? So structures that roughly speaking tell you about what you can observe of this piece, but these observations don't usually obey any functional relationships. So you can't say, you know, everything here are inputs and everything here are outputs. It's not normally that simple. So for all these reasons, maybe we should sort of discard terms and replace them with something more interesting. So one solution which has been popular, I would say, in the last 15 years or so, is that we can study all kinds of various ways of restricting the kinds of terms we are allowed to write. Things like linear type theories that might force you to be careful and only use some resource, let's say once. But I would say that this doesn't address all of the limitations of classical terms that I've identified on the previous slide. And my favorite solution is to make the jump from terms to string diagrams. And when I say string diagrams in this talk, I always mean string diagrams for symmetric monoidal categories. Okay, so this is a very pretty graphical syntax to talk about arrows in a symmetric monoidal category. So of course that's, I'm going to try to convince you why this is a good thing to do. But of course, one problem with doing this is that, you know, we have 1,000 years of tradition of working with terms computationally. There's not as much work, you know, obviously there's a fraction of the work that's been done for string diagrams. And so we need to understand how to do this better. And this talk and this whole research program that I've done with my co-authors is really about some rewriting in this setting. And this is what this talk will be about. Okay, so let me just justify a little bit more why I think string diagrams are a very natural place to look for something that replaces terms. Well, first of all, it's a conservative extension of classical terms. So basically what I mean by this is that anything that you used to do with classical terms, you can do with string diagrams. And why is that? Well, I told you this thing that, that classical terms, one way of thinking about them is as a convenient, concrete representation of the arrows of a category with free finite products. So there's this very beautiful theorem due to Thomas Fox in the 1970s that a category of finite product is actually the same thing as a symmetric monoidal category with a commutative comonoid structure on objects that is natural and coherent. So I'm just going to explain to you very, very briefly about what this means. So we're going to stick to the free category on one object, right? So the idea is that we have one type of things. And over here, on left, I have the kind of structure that I'm assuming I have, right? So I have this thing which I'm going to think of as a copier, and this thing which is a deleter. The copier and the deleter have to satisfy the equations of commutative comonoids. So that's co-associativity, commutativity, and unitarity over here. And naturality basically means that anything is copyable, right? So if I have some f here, some string diagram, maybe some operation, and I copy, well, it's the same thing as copying first and then performing them after the copy. And if I do something and then I discard it, well, it's just the same thing as if I discarded it from the start. So these two equations are what I call naturality here. So basically the idea is that if I have a string diagrammatic language with this kind of structure, well, it's really the same thing as what you're used to with classical terms. And I'll give you just a very simple example to give you a feel for how this works. So I'm going to assume the signature of monoids. So I have an operation M, which is a binary operation, and an operation E, which is a nullary operation. So this is a constant. And here on the left, I have a term in this theory of monoids, which, okay, would typically be written in fix. Here I've written it out. So x is a variable. And the way I think of this as a string diagram, and this is a bidirectional transformation here, is the idea is that this wire that's coming in on the left represents the variable, the variable x. Okay, and you see that the variable x here occurs twice in the term. So essentially, I copy this variable using my comonoid structure, which I have around, and then I essentially just plug everything in as it's plugged into the term, right? So I don't really want to explain too much in words. I think it's more beneficial just to stare at this and convince yourself how this correspondence works. It's quite intuitive, I think. Okay, and once you have this translation in mind, then we can just translate our traditional equations over here. Let's say these are the equations of commutative monoids. So the equation of commutativity, associativity, and unitality. I can translate this as equations between string diagrams. Okay, so I'm essentially saying really the same thing, except the symmetric monoidal structure is taking care of the of the variables for me, right? So this is mxy, and here I want to sort of reverse the variables. So first I did the symmetry in my symmetry thing in the string diagram. I swapped the two i's. Okay, so that's essentially how the correspondence works. Now I have to, if I'm just going to think of this as a vanilla symmetric monoidal category, then I also have to make sure that the string diagrams will behave like terms, right? And this is what I was telling you about on the previous slide, that these equations have to hold and naturality has to hold, right? So I have to make sure that the copying structure is a commutative comonoid. And here I also add the equations for naturality, right? So this is basically saying, the first equation here is saying that the multiplication of the monoid is total. This is saying that the unit is total, so the unit is a natural element. And this is these two equations are saying that the multiplication is single valued. And this is saying that the unit is single valued, right? So these two equations together for the unit just basically tell you that the unit is a singleton element. And using this kind of recipe, I can translate any algebraic theory into this kind of monoidal theory, for which I have a syntax with string diagrams that obey these laws. Okay, and this kind of point of view extends, so I'm just going to very quickly advertise a Paweł 21 paper with Fosco Lorojan, Ivan de Liberty, and Chad Nestor. So previously we were talking about, so this setting here, this is a traditional setting of algebraic theories, or Lovia theories, if you like. We can extend, so we can now use the power of string diagrams, right? Because with terms, you can only go so far because of these underlying implicit assumptions that I've told you about. But of course, with string diagrams, I can be much more flexible. And in particular, we showed, one of the things we showed in this paper was a Fox-like theorem, where we, instead of characterizing categories of finite products as certain symmetric monoidal categories, we characterize these things called discrete Cartesian restriction categories, which are particularly useful when you want to talk about algebraic theories with possibly partially defined operations. Okay, so these partial algebraic theories. So this is what we showed in this paper is this is a symmetric monoidal category with the copying structure that we've seen before, but also this additional guy here, which we think of as a partial equality check. Okay, and we have the commutative comonoid equations that you've seen before. We want this equality check to be associative and commutative, and also the copy and the equality check together satisfy these equations, which are actually quite famous equations. These are known as the special Frobenius equations. And now for the naturality, we only require single valuedness, right? So we only require naturality with respect to the co-multiplication, the copier, but not necessarily naturality with respect to the co-unit, the discard. And in particular, those operations which are natural with respect to discard are precisely the total operations. Okay, but anyway, so just as before, we've kind of carved out this class of string diagrams that allowed us to talk about classical algebraic theories. Now we have a class of string diagrams that allow us to carve out this class of partial algebraic theories.
Paweł, can I ask a question here?
Sure.
Just in terms of the syntax here, or how that relates to traditional ways of specifying partial algebras, would that be like an existence equation? Or what is the
so what happens? So there's all kinds of various ways that these have been traditionally done, right? So there's this formulas of essential algebraic theories. There's a formulas of finite limit sketches. But essentially, the idea is that that we can pack in equations. I mean, maybe I can show you some examples after the talk of the various things you can do with this. But essentially, the idea is that with this partial equality check, I can also add to my equations the power of talking about domains of definition. Mm-hmm. And that's really, and that corresponds to something like, for example, essential algebraic theories. When you look at how that's done, is that we have sort of equations between terms, but also equations between domains of definition. And
okay, thanks.
But you know, what I really like about this is that sort of everything now is just packed into this, right? I don't need to create, I don't need to work hard to make everything work with ordinary terms, because we know that ordinary terms are not supposed to be used for this, right? Somehow. So this feels to me like the right thing. And I've also worked a little bit with Filippo and Duško Pavlović. And recently, my PhD student Chad Ness has been working on this and worked out a really impressive variety theorem for things that are relational theories, right? So now operations might not only be partial functions, they might actually be relations. I don't want to say too much about this because it's not really the point of the talk, but this turns out the categorical notion here turns out to be something called the Cartesian bicategory of relations, which was originally introduced by Aurelio Carboni and Bob Walters in 1987. I mean, here you can see that again we're sort of extending the syntax, right? So this is the stuff you've seen before, and now we also have units. We still have this these special Frobenius equations. We don't have any kind of naturality now, but one way one way you can present them is to say that this kind of thing is idempotent. So some people call this convolution. So convolution is idempotent. And so this gives you a nice syntax now for algebraic theories, for relational algebraic theories. Okay, and of course, this is just a part of the story, right? So these string diagrams have been used for many different applications. Bob Cook and Ross Duncan started off this idea of the ZX calculus, which is a calculus for reasoning about quantum foundations, quantum computing. This has been extended in all various directions. So this is an active research area. I got quite excited a few years ago about doing linear algebra with string diagrams, so I even wrote a blog about this. And there's a whole bunch of other work, which I think I'm just going to flash in front of your eyes and not go into because I'm spending already way too much time on this. So let me tell you what this talk is really about. Well, I want to now, why are terms so great, right? I mean, why have they been so great since Fibonacci? Well, because when you want to sit down and calculate, we understand how to do this, right? So let me just tell you how I calculate with string diagrams, how I write proofs with string diagrams. And this is often called string diagram surgery. Okay, so the idea is we're going to write a very simple proof with string diagrams. And I'm going to prove that in this particular way of presenting commutative comonoids, I only gave one direction of the unit law, right? I only gave you this as an axiom. I'm going to prove also that if I put the unit on the other side, it cancels out. Okay, so the idea is that first I'm going to use the laws of symmetric monoidal categories to pull this co-unit across, right? So these are equal as string diagrams, right? Because string diagrams, essentially, especially in symmetric monoidal categories, the way you should think of it is if you can sort of, continuously deform one into the other, they are equal. So we first deform it like this, and now we can find the left-hand side of one of our equations, which is the commutativity equation. So now I can replace the bit here in this dotted yellow box with the right-hand side, simplifying my string diagram. And now again, I can find the left-hand side of one of my axioms, which is the other unit law, which I can now replace with the identity, right? So I've performed a simple proof, I've performed a simple calculation. And the way this works really is when you try to generalize, is that if I have an axiom, something like L is equal to R, then I can replace A with B when I can find L as living inside A, right? So I can find this context of A1 and A2 with some L, with the L living inside, and then I obtain B with the L replaced by the R. Okay, that's the basic idea. And just as I can turn an equational system on terms into a rewrite system, I can, of course, obtain a rewrite system on a symmetric monoidal category in this way. I basically just orient my equations now, right? So instead of saying L is equal to R, I say that L goes to R. And it's exactly the same thing as you saw on the previous slide, except now there's a typo because instead of B1 and B2, this should be A1 and A2. I forgot to fix this typo from Monday. Okay, so that's the basic idea. But this is all fine when you're working with pen and paper, right? But the question now is, for example, if I want to implement this on a computer, how do I do this, right? So how do I actually come up with the appropriate data structures, the appropriate algorithms to make this work? And when you look in the literature, you know, the way that string diagrams have been formalized, so there's for example, this famous work by Joyal and Street. The way they're described as topological objects, right? So they're not particularly obvious. It's not particularly obvious how to turn these topological descriptions into something you can actually, you know, into something like a data structure. And that brings me to the second part of the talk, which is we'll see how to relate string diagrams with graphs, in particular hypergraphs. And this is kind of the central technical observation that I want you to take away from this talk, right? There's this kind of a nice theorem which gives you a bridge to pass between string diagrams on the one hand and hypergraphs on the other. So first I'm going to tell you what I mean by a hypergraph. So first of all, a hypergraph is something which has vertices and edges. I'm going to say this is a directed multi-hypergraph, right? But I'm just going to call this hypergraph. So V is a set of vertices and E is a set of hyperedges. So what's a hyperedge? Well, it's kind of just like an ordinary edge in a directed graph, but instead of having just one source and one target, we can have a word of sources and a word of targets. Okay, so we have a whole bunch of, this is a hyperedge, a particular kind of hyperedge, which has, you know, M inputs and N outputs. And these inputs and outputs are ordered, right? So the order matters. And this has an obvious notion of homomorphism. So, you know, vertices go to vertices, edges go to edges, except of course, you know, the types of the edges. I have to take an M to N hyperedge to an M to N hyperedge in the way that everything is preserved as you'd expect. So the nice thing about here, this category of hypergraph and hypergraph homomorphism, is that it's a appreciative category. Essentially, this is not very surprising when you think about it for just a few moments, right? Because we know that the ordinary category of directed multigraphs is a appreciative category. And this guy is an appreciative category in very much the same way, except for instead of one object for edges, now we have natural numbers times natural numbers of these, right? Because we have, this is the object of M to N hyperedges with the corresponding number of source maps and target maps. So the good thing about this being a appreciative category is that we know that it's very well behaved. In particular, it's adhesive, which is going to help us to, do DPO rewriting on this. So that's the category of hypergraphs. I just want to tell you what sigma hypergraphs are. Well, sigma here is some monoidal signature, right? So the idea is that it's a bunch of operations with arities and co-arities. And I can identify any such thing as a one vertex hypergraph, right? So each edge is basically, like each edge corresponds to something in my signature sigma. And now hip sigma is just simply hypergraphs typed over this, this signature. And people familiar with graph rewriting have seen this kind of thing many times before. So this is my category of sigma hypergraphs. And now I want to explain to you sort of the main, excuse me, the central theorem here. So cospan, so this thing which I'm going to call CSP hip sigma, so cospans of hip sigma, this is a prop. It's a particularly simple kind of symmetric monoidal category. Everything's strict. My objects are just natural numbers. So the idea is that the arrows from n to n are going to be cospans, or actually isomorphic classes of cospans, like this, right? So I have a hypergraph in the middle, and I have kind of an input handle into the hypergraph. So you think of this as a discrete hypergraph with n vertices. This is a discrete hypergraph with n vertices, and this cospan is kind of like this hypergraph with some vertices identified as inputs and some vertices identified as outputs, if you like. And we compose them by doing the push out in the category of hypergraphs, which essentially just means gluing hypergraphs along this common boundary. Okay, so that's the first ingredient that I wanted to tell you about. The second ingredient is kind of this walking theory, this walking symmetric monoidal category of special Frobenius algebras. So if you like, this is just the prop that I obtain from the signature, where I have the copy and the the co-copy, if you like. So the co-monoid structure, the monoid structure, where the monoid is commutative, the co-monoid is commutative, and I have these special Frobenius equations. So what is the central theorem? So the central theorem says this. So let S sigma be the free prop on the signature sigma, right? So this is really somehow the thing of which a nice description of this guy is that the arrows of the free prop on the signature are precisely string diagrams. Okay, so this is the arrows of this guy are string diagrams, and so this is an interesting thing for us to look at. And this theorem here gives us kind of a bridge to be able to translate between string diagrams and these combinatorial structures, these hypergraphs with inputs and outputs. Okay, so what does this theorem say? It says that if I take my free prop on sigma and I add a special Frobenius structure, well, this is really the same thing as the category of the prop of cospans over hip sigma. And I'm just going to give you a little bit of a taste of how this works, again, just by showing you pictures. Okay, so essentially what this theorem says is that I can, for a particular kind of special class of string diagrams, those string diagrams in which I can sort of identify a chosen Frobenius structure, I can translate these string diagrams into cospans and vice versa, right? So this is an isomorphism. So let's just take my sigma to be the signature of monoids, okay? So I'm just going to draw them as these unfilled circles. And so now this is a particular string diagram in my theory. And you see that the cospan here will look like this. And the idea is that sort of the input wire and the output wire are going to correspond to vertices which are picked out by the input boundary and the output boundary. And inside, you see that the structure of this hypergraph very closely corresponds to the structure of the string diagram. But of course, this theorem says a little bit more than just this, because over here, we also have this Frobenius structure, right? So how does this Frobenius structure correspond to what happens on the right-hand side? Well, what happens, for example, here? So we copy and then we perform this this addition operation, or this binary operation that we have around. And so what that corresponds to in the cospan is that both the tentacles are connected to the same vertex, okay, and everything else is as before. This is one more example here. This is a string diagram without any boundaries, right? So it's going to turn out to be the cospan with you know, 0 input vertices and 0 output vertices. But here I just have a single binary operation. Everything else is kind of connected by my Frobenius structure. And this will turn out to be the hypergraph where sort of both the input tentacles and the output tentacle are connected to the same vertex. Okay, so hopefully again, I mean, I think it's kind of more useful to stare at the pictures here than to, you know, try to explain this in words. But this is a nice result because in this particular case, it allows us to really map from string diagrams to these quite concrete things, right? So I can sit down and write a data structure for such things here on the right. So because of this isomorphism, rewriting in S sigma plus Frob is the same thing as rewriting in CSP hip sigma. And of course, this goes back to some work in the 90s by Fabio Gaducci and Reiko Heckel. We understand what rewriting in such a thing means. Well, it's basically graph rewriting. Okay, it's graph rewriting, but what kind of graph rewriting? And it turns out that the right notion is this thing called double push-out rewriting, so DPO, with interfaces. And this kind of thing has been studied in the graph transformation community. I'm starting with this paper by Gaducci and Heckel, which I mentioned. There was some work by Hartmut Erik and Barbara Koenig on rewriting of borrowed context, which used very similar structures. And I was also interested in such things when I was doing my PhD. But somehow, as I told you at the start, it was only sort of started to make sense in my head about 6 years ago that these two things were actually connected when I was doing graph rewriting all along, right? So it's one of these situations where you try to escape, but they pull you back in. So for the people, for the extremely small probability that there's somebody in the audience that doesn't know what DPO means, I have this slide. When I was talking to category theorists, I spent a bit longer here because, you know, not all category theorists know about this. But I think with this community, I'm going to be very quick because you've all seen this many times. So you know that in DPO, our rules is span of morphisms. An application, to do an application, I need to find a match and I need to construct two push-out diagrams. So operationally speaking, I need to find a match, I need to construct a push-out complement and then construct a push-out in order to get a rewrite. So let me tell you how, let's start doing some DPO rewriting, and I'll try and sort of give you an intuition of how that corresponds to doing rewriting in S sigma plus Frob. Okay, so here I have a DPO rule, which corresponds to a directed equation between string diagrams that tells me that, you know, this is a binary operation, this is a unary operation, and this guy is a unit for this guy, right? So this guy rewrites to identity. Okay, so this is a rule that tells me this. You know, here's a larger context in which I can find the left-hand side. I can perform the double push-out rewrite here, obtaining this guy. Okay, and just to give you a comparison string diagram surgery calculation, well, this guy here, when you stare at it, it's really telling you, it's talking about this string diagram over here, right? And here I can find a match in the left-hand side and replace it with the identity. And this is now the result of performing this double push-out rewrite rule. Okay, so this is just to give you the flavor of why this works. I have this example which I think it's useful just to spend a few minutes, well, probably I don't have very much time left, but okay, let's just spend a little bit of time on this because it's quite important for something that's going to come a little bit later in the talk. So one of the things that I somehow maybe traditionally have been a little bit annoying about double push-out rewriting is that the match doesn't always determine the result, right? So it might happen that there is more than one push-out complement. And it turns out that to actually be quite relevant here. Okay, so I'm just going to give you a very simple example. So here I have a rule that if I think of it as a string diagrammatic rewrite rule, it will tell me that I can replace the identity with some unary operation. Okay, I can replace x with f of x, where f is this red box. Okay, and now I'm going to find a match in this diagram here. And it turns out that I have two different push-out complements. So essentially, in order to perform this push-out complement, I have to kind of, tear this connection apart over here. But I can tear this connection apart in two different ways, right? I can map the one here in the context to the input, or I can map it to the output.
Sorry, excuse me, Paweł. Can you use a bigger pointer somehow? It's sometimes difficult to see where you're pointing.
Yeah, I'm sorry. I don't really understand how I can do this. But maybe I can just talk you through it. So yeah. There are two different things here on the diagram. So maybe now look at first let's look at just the yellow arrows. If you look at the yellow arrows, that's an example of a double push-out rewrite where I found one push-out complement. Okay, so this is a push-out complement. Now if I glue the blue and the red, I obtain this guy here. But if you now look at the green structure, this is a different push-out complement. Okay, well essentially I've reversed where the 1 and 2 map to. And now I can again perform this push-out, but I'm going to glue the red guy the other way, right? So backwards. And this actually has a corresponding reality when you're talking about, a free prop with a chosen special Frobenius structure. Because if I have a rewrite rule that takes an identity to this red guy over here, then I can perform this rewrite, for example, over here, which is this top rewrite here, this top string diagram surgery corresponds to the yellow double push-out. But here I can also use the special Frobenius structure to kind of introduce this additional loop in my diagram, and they're equal now just by the laws of special Frobenius monoids. And now I can perform the rewrite on this top wire that has just sort of appeared here to obtain this diagram. And this is another different string diagram, right? So this is a different arrow. And this is just to give you a little bit more flavor of how this isomorphism works. It's a very close correspondence. Is that clear, or is there any confusion? No? Okay, so and because this is DPOI, I just wanted to remind you what these interfaces mean. It just means that instead of rewriting hypergraphs, I'm going to rewrite hypergraphs with an interface. Okay, an interface is just some chosen vertices. And I guess most of you have seen this too. I mean, the idea is that you have your standard double push-out diagram, but you have these additional two triangles that tell you that sort of your handle onto the graph stays along as you perform the rewrite. So these two triangles commute. Okay, so the upshot here is that we know that rewriting in cospan of hip sigma is really just the same thing as DPOI and hip sigma. And I think this observation was first made by Fabio and Raiko. And what that means is that I'm now going to translate essentially my string diagram rewrite rules into these double push-out rules, essentially in this way. And performing rewrites will really so performing a rewrite of a string diagram with boundary mn will turn out to correspond to this DPOI rewrites where the interface is M together with N. Okay, and again, I think it's just better to stare at this for a few seconds than me to keep talking. And I hope that's at least intuitively clear how this correspondence works. Okay, so this brings me to the final part of my talk. I think how much more time do I have, Raiko? Okay, can you hear me?
Sorry, I was muted. So, well, we have about an hour for the actual.
Okay, so let me try to do this one a bit quicker. I'll try and finish this in 5 minutes or so. But this is the final part of the talk, and essentially, what I've told you so far is the wide part of this slide, right? I've told you that rewriting an SMC with a special Frobenius structure is really the same thing as DPOI on hip sigma. Okay, but I started off. But we have many examples. We have many examples that have special Frobenius structure, but not all. Right? Let's say if I want to do classical algebraic theories, I don't have an entire Frobenius structure. I just have the co-multiplication and the co-units. Okay, so what I really want to understand is, how do I do rewriting in vanilla SMCs? If I just give you a symmetric monoidal category, if I just give you some prop, if I just give you some class of string diagrams and want to perform the string diagram surgery, then how do I implement that? So it's going to end up being a restriction on the kind of DPO that you're able to do. Okay, we call this thing convex DPO rewriting. So I'm just going to give you very quickly an idea of how this works. And there's some technical examples here. I don't particularly want to, I think I'll just go through it quite quickly. So the first thing that happens on this wall of text is, let's go back to this theorem that I told you about, that S sigma plus Frob is the same thing as cospan of hypergraph sigma. Well, because this is the case, I have these two coproduct injections. This is a coproduct diagram, right? So it's interesting, first of all, to understand what is the image of S sigma in these cospans, right? So which of the cospans correspond to vanilla string diagrams that don't use any Frobenius structure? Okay, and it turns out that these are precisely the monogamous acyclic hypergraphs. So monogamy basically means, I'm not going to read this, but it essentially means that any vertex in my hypergraph has one thing connected as an input and one thing connected as an output, right? I can't connect multiple, let's say, input ports to the same vertex. I can't connect multiple input tentacles into the same vertex. So everything has to be one in, one out. Okay, so that's the idea of monogamy, and of course acyclicity is what you'd expect. So this is a nice characterization of this image, which now allows us to say that these are the kinds of cospans that I'm interested in, right? Because I want to now throw away this Frobenius structure. I don't want it. Another thing is that if I just do vanilla DPO rewriting, I will allow illegal push-out complements. So push-out complements which somehow rely on the presence of the special Frobenius structure when I think about it algebraically. Okay, and the way to do this is the way to disallow it is to concentrate on a very special class of allowable complements, which we call boundary complements, and we have a characterization of this. Again, it's essentially checking whether a particular cospan is monogamous that you obtain in a canonical way from the push-out complements, right? So if you give me a push-out complement, I can tell you, is this a boundary complement or not? Another little cute fact is that now boundary complements are unique when they exist. Problem two is I have illegal matches. So also the matches can somehow, under the table, sneak in the use of the special Frobenius structure. So here's an example of one of these. Again, I think I'm just going to leave this, and maybe if you want to see, we can come back to this in the question. But essentially, the very basic idea is if you look at here, this left-hand side. So this is my rule here. This is this rule encoded as a DPO rule. Now I can match this guy inside this left hand, I can match this left hand side inside this hypergraph, but I'm kind of being naughty here, right? Because this guy is supposed to be an output, this guy's supposed to be an input, but here I've kind of moved the output before the input. And that's bad, and it allows me to perform a rewrite, which is illegal if I don't have this special Frobenius structure around. Okay, and in order to disallow this, we have to insist that matches are convex. So basically, this means that if I have some path between two vertices in my match, in the image of the match, then that path must also be in the match. And here, this is not the case, right? Here I have this purple business, which is connecting two things which are in the match, but the purple guy is not in the match. So we restrict to convex matches. So convex matches are those which are mono and image convex. And now this gives us this theorem that just rewriting in a vanilla symmetric monoidal theory is just this convex DPOI rewrite. Okay, so it's basically DPOI where I restrict my attention to monogamous acyclic cospans, so the things that are actually string diagrams. And when I perform rewrites, I perform them in the way in which the matches are convex and my push-out complements are boundary push-out complements. And that's basically it. So that's we kind of successfully restricted the kind of DPO that I'm interested in order to capture this notion of rewrite. So let me tell you, so this was basically our first paper. So this was published in Lix 16. Since then, we've been thinking about all kinds of extensions. So we have a paper about confluence. There's a lot of interesting things to be said about confluence, which sort of maybe is a little bit counterintuitive if you know about the work of Plump. We've also thought about sort of the if you like the multi-sorted version, which is this rewriting Frobenius. And recently we've been putting together these journal papers, which I think that the third one I'm supposed to be working on Sunday because we're almost at the deadline. So this is my final slide. So thank you so much for your attention.
Okay, thank you very much. Any questions from anyone? Or can I, otherwise I start and let people sort of digest a bit.
I'll ask a question.
Oh yeah, please go ahead.
Yeah, so the DPOI, convex DPOI gets you back to SMCs.
Yeah.
It seemed like a lot of the problems came from the fact that you were working in HIP sigma, which is a pre-sheaf category that was like hypergraphy, and so like hypergraph category axioms came into play in the rewriting. Could you change the indexing schema for the pre-sheaf category from HIP sigma to some other pre-sheaf category to put the structure in there, rather than putting the structure into the matching and the boundary complements thing? So here, yeah, this is like change. I guess X is this is like a bold X.
Yeah. It's an interesting question. I'm not. So first of all, let me say that the Frob here, the fact that we also get this additional Frob structure by considering this category, I consider this a feature, not a bug. Right? Why do I say that? Is because we also there are a lot of applications that have this Frobenius structure around, right? So you can then use this isomorphism, and now you have rewriting not only modulo symmetric monoidal structure, but modulo symmetric monoidal structure and a chosen special Frobenius structure, right? So this is this to me is a feature, not a bug. But let's say I'm interested only in the vanilla SMC case. Can I restrict this guy in some way? I don't know. I haven't really thought about it. If you have some ideas, I'd be interested to hear.
Yeah, I see how to implement DPO rewrite. I guess what I'm going to talk about in my talk next in the series is about kind of implementing stuff for arbitrary pre-sheaf categories where the indexing schema is finite. And so you can kind of we have like matching and push out complement and stuff. So I see that. And we found in our applications that adding structure to the indexing schema is much easier than writing new algorithms or adding complexity into the algorithms. So I think that keeping matching simple would be easier than and I don't have an idea of how to change the schema to achieve this effect, but maybe distinguishing the inputs and outputs more or something like that.
Yeah, it could be, but I mean, I was still, since this is a pre-sheaf category, this should still fall into your framework then, right?
Yeah, I am thinking about, could I actually have this done in a month to talk about?
Excellent.
It should work. Yeah, of course, it would be bounded degree.
Yeah, well, it's only HIP that has unbounded degree, but really, when you think about HIP sigma, you're restricted to a particular kind of things that are in your signature, right? So then you're only interested in finitely many such big E's, right? Because you're only interested in the ones that sigma you have in theory, right? So
yeah, you want.
Let's say for the monoid, let's say you're only interested in monoids, right? Then you only have, a 2-to-1 hyperedge and a 0-to-1 hyperedge, and then if you want the Frob, you would add some more. But for all applications, this would be a finite thing. So.
Right. Yeah. If the signatures are of bounded arity.
Yes.
Then,
yes. Of course.
But
you have boundedly many things that you have bounded things in your signature. You have a finite signature.
Yeah. This is very exciting and exactly what we've been looking for on actually implementing a lot of like graphical linear algebra and stuff. We need to do rewriting on string diagrams.
Well, actually, I was thinking about this for some time. I never actually wrote anything down, but one should be able to, let's say in graphical linear algebra, you have two different Frobenius structures. So pick one of them as your chosen one, and now you've just got vanilla DPO, right? So that could also be kind of interesting for computational stuff if you want to compute, do linear algebraic computations. I don't have any experimental, experience with this, but could be
definitely
to implement.
Yeah, I've definitely implemented enough of it to know that it can be made to work. There's a lot of engineering to actually make it fast, but as far as being a better way of doing linear algebra software development, it's viable.
Nice.
So I'm very excited.
Excellent. Well, we should talk more because I'm also working with this guy called João de Paixão from Federal University of Rio, and he's got a whole group of students there who are sort of playing around with graphical linear algebra and doing all kinds of exciting stuff. So
yeah, I'll follow up by email.
I would love to explore the computational aspect.
Well, we have a bit of time afterwards in the informal discussion
sure.
to come back to that as well. But I see that we have a couple more questions. So Jonathan, do you want to unmute yourself and ask that?
Sure, thank you. Well, so first of all, Paweł, I think it's a really great idea. This general notion of you have some Frobenius structures, but somehow you can absorb them by passing into this hypergraph case, and then you just do bare metal SMC rewriting, which kind of just encodes the structural aspects. I think that's a really nice way of setting it up. So I guess my question actually follows on directly from James, or the comment you made about James's, which is, for most of the kind of actual applications that we care about, like graphical linear algebra or ZX calculus or whatever, we have multiple Frobenius structures. Mm-hmm. And the setup you've described here with prop, which is of course single sorted, presumably can only absorb one. And
yeah,
so
this is exactly what this third part of the story is about that I haven't told you anything about. But this is what I refer to as the multi-sorted case. Uh-huh. It's rewriting of Frobenius. If you look at this paper, this is where we consider having several Frobenius structures.
Right.
So we have thought about this, and it's an interesting. I agree that in several applications you have not just one special Frobenius structure, but several. Yeah, and then you can basically, to answer your question, is that it ends up being something like hypergraphs with two different type vertices.
Right.
You have to, there are all kinds of, I mean, I don't want to sort of oversell the simplicity of it. There's a few sort of technical bits, but that's the basic idea.
Okay, but can I think of this as being like some kind of non-Cartesian analog of like a multi-sorted Lever theory? Like,
Yes,
are you
exactly.
Okay.
That's how I think of it.
Right. Okay. So basically, you've got some strict SMC, and its monoid is freely generated by some set of colors, and there's one color for each algebra.
Exactly. For each sort, exactly. Mm-hmm.
Okay. And so in that, how do you guarantee sort of functoriality between the, between the colored props that you're dealing with? Presumably, there has to be some kind of isomorphism between them.
Yeah. So I don't really know how much detail I want to get into this. Maybe we can get into it a little bit more offline, because.
Fine. Sure.
But yeah, so we have worked out a part of the story. Yeah.
Okay, that'd be very interesting to hear about. Thanks.
Okay, thanks, Jonathan. Francesco, you want to go ahead, ask your question?
Yes, thank you. So I have a general question on string diagrams, actually. So when we work with terms, we do not only have the, let's say, syntax for algebraic terms, which are the one you talk about. We also have a term-like syntax for higher order things, such as in the lambda calculus, for instance. I was wondering, is there something similar also when you move to a non-Cartesian or string-like setting?
So I'm just going to challenge you a little bit. I mean, so lambda calculus is more than just ordinary terms, right? So it's terms indeed. With binding and when you think about it, sort of lambda calculus can be understood. Well, let's say the simply typed lambda calculus. That kind of syntax can also be understood as giving a nice description of a free category of some kind, right? It's this free Cartesian closed category. I don't know how much of that sort of higher order can be told, let's say at these more, I mean, so for example, in the relational case, right? So in the relational case, we have these things that are called Cartesian bicategories of relations, and these are already closed, right? So that somehow you have the compact closure, but it's a very different kind of, I mean, it feels like a very different kind of closure to the Cartesian closure. One thing which could be related is when you look at the string diagrams for relational theories, they turn out to very closely correspond to what you can do in regular logic, right? So you have regular logic is this part of first order logic where you have the existential quantifier and the conjunctive structure. Now, one question is, how can we take string diagrams one step further from regular logic to full first order logic? Okay, so this will be something like adding negation or adding the universal quantifier. So in category theory, the way one would do this traditionally is to think about something like hyperdoctrines, for example. But when you look at the diagrams, then actually the answer was already given at the end of the 19th century by a guy called Charles Peirce, who discovered this notion of beta graph, which is a string diagram of negation. And so that's certainly something really quite fascinating and something which one of my PhD students, Nathan Hayden, is working out. But I mean, one thing is, I mean, you can, for example, formulate the notion of Cartesian closed category as a partial theory. So that would be in that sort of second part of the hierarchy. So somehow you can talk about binding internally, but it's not really built into the syntax as a special operation. So this answer is taking forever. Let me just finally say that there is some really interesting work on string diagrams for symmetric monoidal closed categories and related work on star autonomous categories. That goes back to Todd Trimble and various people. Also, Richard Gardner's done work on this. Tom Hirschowitz has done work on this. And there you have, and this is closely related to when you look at the string diagrams, it's closely related to linear logic, to parts of linear logic, right? Because so essentially what happens is that in your signature now, instead of having just a tensor product, you have the tensor product in some kind of lollipop, right? But then you need to know that your string diagram respects binding in the appropriate way. And that goes back to something called the Danos-Renier condition for proof nets in linear logic. So I find this, there are these connections, but that would go beyond the kinds of string diagrams that I've talked about here, because I've really concentrated on the symmetric monoidal case.
Okay, thank you.
Okay, thanks. Yeah, we have another question by Paul-André, and then I think we probably have to close and take it to the informal part. So, Paul-André, you want to go ahead?
Yes, please. Thank you for your very nice talk.
Hey, Paweł.
Paweł. Yes, nice. So I was just wondering about your new conditions that you gave. So if you come back to them, and so I mean convexity and this, like these two conditions you added, yeah. And so I was just wondering whether you have for boundary complements and so nice let's say categorical algebraic descriptions of them, and whether these specific squares, they have nice compositionality properties or of that kind. I mean, because this is one of the strengths of the DPO approach, yes, that you have all these very nice properties for example, for push-out complements. So I mean, so my question in a way is, are these definitions very specific, or do you think you can give some nice, or maybe some nice abstract characterization of them? Yeah, that's my question.
That's a very good question. So we certainly haven't really. So in the paper, it's very specific. We really talked about hypergraphs, right? Because that was what the this theorem that gets you from this algebraic structure to the combinatorial structure, if you like, told us to focus on. But sort of generalizing this notion of convex DPO, I would say it's definitely a very interesting thing to try, but we haven't really thought about it. So it's that will be certainly a really interesting project, I think, to understand what's really going on here at a deeper level.
Okay, wonderful. Thank you.
Thanks, Paul.
Okay, so thank you very much, and yeah, thanks, Paweł, again for that nice and sort of illustrating talk, and
thank you.
I still liked your slides. So even if they were slightly not
were they readable?
It was good. It was nice to read. So yeah, thanks everyone for attending and for the nice discussion. And I think we close the official part here and sort of remain for chat. Okay, thanks.
So thanks, Paweł, also from my side. I'll just briefly close the YouTube stream. So just for anybody who's on YouTube still and would like to join the discussion, you will find the Zoom link on the chat, because we will keep